So we started with this 12-hour clock because that's the clock that we all know and use. But it turns out that if we change to a different size clock, things actually work out a lot cleaner. So prime-sized clocks in particular make fields. The four basic operations on this clock, if you sort of just make a multiplication table, subtraction will undo addition, as you would hope. Division will undo multiplication, as you would hope. Every number has a reciprocal. In this case, 2 times 3 is equal to 1. So 2 and 3 are each other's reciprocals. And 4 is its own reciprocal on this clock. So here's the multiplication table on this clock. I think it's relatively clear what you would need to do in order to construct the entries here. So I'm not going to spend too much time rehashing what would 3 times 3 mean on this clock. If you understand what 5 times 5 meant on the other clock, then I think it should be pretty clear what 3 times 3 means on this clock. So I have this little multiplication table off to the left. And I similarly marked it with the orange zeros are what happens when you multiply by 0, and the blue row and column there are what happens when you multiply by 1. So we have on this clock an additive identity of 0. We have a multiplicative identity of 1. And this multiplication table, I want to just sort of play with a little bit more. I want to take away the 0 for some reason that I won't say too much about. Now, when I look at this version of it, it sort of pops out to me as it looks like a Sudoku board. Every row and every column has exactly one copy of each element. There's no repeated numbers in any row or any column. And in fact, if I rearrange, instead of writing it as 1, 2, 3, 4, I feel like if I instead write it as 1, 3, 4, 2, then it looks not only like a Sudoku board, but it actually looks just like an addition table now. If you sort of look at the shape of an addition table, the diagonals line up in exactly the way they do here. This is not a coincidence. If I take any finite field and I remove the zeros, or take the multiplication table, I should say. If I take any multiplication table for a finite field and I remove the zeros, it's going to look like a Sudoku board. And if I can find the right way to rearrange the numbers on the top or on the edges, I can make it look like an addition table. And here's the sort of cleverness that you need in order to find the rearrangement there. It turns out that these numbers on this clock can all be seen as a power of 3. 3 to the 0th power is 1. 3 to the 1st power is 3. 3 to the 2nd power would be 9, but on a 5-hour clock, that becomes 4. And 3 cubed would be 27, but on a 5-hour clock, that becomes 2. And if I fully rearrange my multiplication table in terms of...
by the way.
Sorry, what?
There's a hand raised, by the way.
Oh, great. Yeah, let's hear the hand. Thank you, Tim. Is there a question?
Yeah, just a quick one. I'm not seeing the addition here. Could you kind of explain the addition?
Sure.
Where it's like an addition table? I'm not.
Yeah.
I mean,
yeah, no, absolutely. Take a look at the far right column here, or the far right table, and imagine there were no 3s. Then, like the exponents that are written here, I have 3 to the 0 times 3 to the 0 is 3 to the 0, which functionally is 0 plus 0 is 0. I guess I could also, if you look at a typical addition table, these diagonals. Oh, do I have a error in my, am I? Maybe it doesn't actually look like an addition table until I rewrite it in terms of the exponents.
Yeah, I guess I'm kind of seeing it now. Like you're saying, like, look at the diagonals. So, like, for example, you pointed at 2, 2. So 2, 2, then diagonally makes 4, and then I guess 3, 4, but in 5 and mod 5, it is 1. I guess somewhere.
I pointed at the diagonal in the wrong table. The middle table doesn't look like an addition table. It's the far right table that looks like the addition table, and so that I apologize for misleading you in answering that question.
Okay.
But if I step back to here, the diagonals here are all actually equal to each other, right? They have a diagonal of 3s, a diagonal of 4s, a diagonal of 2s, a diagonal of 1s, a diagonal of 3s. And this really, I think here, erasing the 3s, we're literally looking at an addition table. If I erase the 3s and change the x to a plus, this table will be 100% precise. Well, up to the...
Okay, I think
the end has a little bit of wraparound issue, I guess.
I guess this makes sense, because I guess in multiplication, exponent is addition. Is that kind of the point to?
Yeah. Yeah. The sort of, if I'm thinking in terms of a single element and I'm looking at powers of that element, then when I multiply them together, I essentially just add the exponents. So the kind of real trick of making finite fields feel easy is you can always find a single element to focus on and just say everything else is just some power of that element. And that element that's here, it's 3, is called a generator. So to summarize, and you ask a really good question here, because the addition is a little bit hard to see initially. But the key sort of magic of finite field arithmetic is that if you think of everything in terms of a generator, then multiplication just becomes effectively adding the exponents of that generator. So this is something that is maybe a little bit, this is a pretty abstract part of this. Up until now, everything's been pretty concrete. I've been able to really explicitly show the examples here. I'm asking you to take a little bit on faith that if we took a, say, clock with 7 numbers instead of 5, that we would still be able to find some generator. And if we rearranged our multiplication table in terms of that generator, things would look essentially just the same as they do here. Is that
the generator has to be a prime number?
It's a great question. And given a particular field, the question of how to find the generator is something that I'm not going to dive into. There will be a generator in any given field. There will be several generators in any given field. The question of, if you're looking at, say, the clock with 47 elements, off the top of my head, I don't have a clear answer to what's going to be the generator for that field. But it's not too hard to just kind of brute force find a generator or ask Wolfram Alpha to find a generator for you. Maybe somebody else has a clear, quick answer to if there's a quick route to finding a generator. I have a hunch the answer is use the Chinese remainder theorem.